All right, Sarah,
Yep.
This episode is so cool.
It really is. We talked to Paul Smith, who's the director of lab demonstrations at the Department of Chemistry here at Purdue, about
Fireworks.
fireworks. Yeah.
So if you ever wondered how fireworks are made, and how they do the shapes, and how they build them, and how they do different sounds, and how they do different colors, he's the man. He has a license to build these, and he walked us through how it works and
Yep.
how they do it, all the science behind it. He explained.
And he also explained how science helped in the advancement of fireworks. So it's a pretty cool episode. It's kind of got it all.
It's really good. We hope you enjoy this one. Thank you.
Today on Superheroes of Science, we are so excited to be in the lab. We are here with Paul Smith, Director of Lecture Demonstrations here in the Department of Chemistry at Purdue. So thanks so much, Paul. Thanks for having us.
Happy to do it. It's that time of year, and we're thinking about that, getting ready for fireworks displays. So talking about fireworks is a good review and natural thing for us to do in that. What you see here is mock-ups of the shells that are used in fireworks displays and in the upcoming season and during the festivals at different times throughout the year and that. So just to give you awareness, one of the things we do is training and safety guidelines and so forth for display companies and things like that. This shell has some live material in it. I've made this up because one of the things we want the trainees to know is fireworks sometimes don't work. And so they got to be prepared for that and so forth. As the backyard fireworks people and doing things there's certain things to be aware of and so forth. So this one is actually made not to work. It will just fly up in the air, fall back down the ground, and that's why it's labeled as DOC training, as Display Operators Course training thing. But you can feel the weight of that.
Oh, yeah.
These are just half of it, so it's going to be different, but you can see how much lighter this is compared. That's made to be more the full weight that you would have in that.
Okay.
So what's live here is this is actually the leader, and this would burn and so forth, and there's actually some black powder in here that would lift it up, so this should perform and actually fly into the air like the shells would do here. You can see comparatively, here's a fake up that was made, and this won't burn, but you can see he's done a pretty good job, and he's just colored string there to create the similar effect to what you would have as the black matte string that's here.
Yeah.
So
looks like the real thing.
this is a 3-inch shell. You see examples here that are cut in half as cutaways of what a 3-inch is like. And you can see here that there's these little beads in there, and he's used different color ones, which makes it easier to see. But the reality is, when you look inside a fireworks shell, it's not, oh, there's the red ones, there's the blue ones, there's the green ones. They're all going to look like this. They're all black.
Okay.
And so there's different effects that are created by this. This is known as a red, white, and blue shell, and that's why I kind of did the different colors. But it would all look black legitimately, and what it would do is throw them out all in rays and give you just a streak of light of the different colors in that. This one here is a chrysanthemum shell, and the idea here is, and one of the titles and names of fireworks shells come from flowers. A lot of the original things came from Japan, and their whole focus on flowers and stuff like that. So this is a chrysanthemum, and so what happens with that, like a chrysanthemum goes out and droops down, you get this kind of drooping, and you can create different colors in that. He didn't say what color. A lot of times they're gold. He just said it's chrysanthemum on that, but that gives you.
So the design and the way they put this together is what makes
Correct.
that?
You see here, these are just scattered throughout, and you have the burst powder, which is the black granular material in here. Is all dispersed around. Here, these are the stars, the little balls, the stars are all to the outside, so it throws them out and creates that chrysanthemum kind of effect.
Okay.
Now, to build the shell up and continue on with the thing, what you have is, we talked about the fuse, and coming in through here, the fire comes into this point. It comes around through the outer package here. You can see it on the outside here, and the bottom here is now black powder that is ignited with that fuse, and the black powder can explode. It is used. It was not as much anymore in blasting if you confine it. What we're trying to do here is restrict it, but not confine it so much, and allow it just to produce a tremendous amount of gas. So what happens is that we take the shell and put it into a tube, and I just happen to have a grad cylinder that's no good because the bottom's broke out, but it works perfectly to be like a launch tube for fireworks. Here's an actual high-density polyethylene launch tube, which you can see there's a wood plug in the bottom that holds it. Generally, these are into the ground 2/3 of the way, or they're in a wood rack and framed and supported inside a rack in that state. But its shell then is lowered into this, and then this lid here, and this works real nice so you can see it inside and how that, so it just sits down there. Well, what happens is, then that black powder ignites, it creates a whole bunch of tremendous amount of gas real quick, that pressurizes a thing, and what do we know from chemistry and physics in that? Opposite reaction to the thing, boom, the shell takes off and flies up.
Okay.
So the process is started, but the trouble is you don't want the shell to explode right here. You want it to explode 300 feet in the air, 400, 500, whatever, and then you get a nice visual presentation. So what you have to have is a timer, and that's what this is here. So the lift powder ignites here, creates a tremendous amount of gas, throws the shell up, and lights the timer.
Okay.
And then that has a delay to it. For a 3-inch shell there, it's going to be a couple seconds at the most or whatever, and that's burning. And so in a fireworks display, if you can see and watch, you can actually see a little bit of a glimmer of light as it goes up. That's the timer.
Oh, so the small thing we see on the bottom, and I've seen these before, and that launches the whole ball.
Correct.
The rest of the ball. And then this is what you're calling a timer, is a separate fuse that's lit this at the same time.
Correct.
Okay.
Got it.
So that gives the proper delay. Then when it burns and gets here, the fire shoots out inside here, and that ignites all this powder. That then explodes the hemisphere, blows it apart. It also ignites the stars, and depending on the configuration in there, then you get the pattern as it explodes out of there. So literally, when you see the real nice pattern things like a heart or a cube or things like that, they've laid it out and they have ways to configure in that pattern inside here, and then they blow it apart in a manner that they all fly out evenly and light at the same time, and that's how you create the pattern. Now you have a little bit more of a challenge in that because you've got the plane effect. So if the pattern is laying like this, you can see it. If the pattern's laying like this and you're looking at it, you're looking at the same plane, and so you're saying, what is that? All you're seeing is the, on the same plane. So we don't know how they're going to orientate the sky. So one of the things they do in pyrotechnic choreography is shoot multiples. One or two of them are going to orientate so the crowd can see what it was, and then they realize, okay, those are 4. I see the 2 hearts, and those other 2 are hearts too, but they're just facing a different way.
Oh, wow.
And it's all in how it's packed together, the rotation.
Correct. And certain people have certain techniques that they know how to make it hold together better and do that. They know how you explode it apart. I mean, some people are all about noise and just making bangs and exploding things and stuff like that. There's more of an art to this to get it to explode in a proper fashion rather than just bust apart. I mean, it's easy to just throw things out and fragment things, but what we're trying to do is create things, paint color in the sky and do that. And so there's a skill to that and so forth. Now, we talked about just making noise and exploding things. That's all this does here. This is a aluminum potassium perchlorate composition that just is very energetic, and so that's where you get the bright flash in the sky and the loud noise.
And this is filled with, not an actual, is it a powder?
Yeah.
And so when those noisy ones that my wife hates with a passion, a passion.
Yep. Some people don't like the noise. They just like the color. Yeah.
That has a powder in it. What is that?
It's a composition of aluminum and potassium perchlorate.
Okay. And when that ignites, it just.
Yeah. It comes real close to being the strength of dynamite. It has that kind of energy out potential.
Oh.
And it has a sensitivity of friction too that you have to be careful with, just the raw powder. So it's a certain amount of mass that when you get to that mass, you light it, it explodes. It doesn't burn. Now, it's not as energetic as high explosives like dynamite and some of that stuff, but it approaches that level because of the energy. Now, notice part of the configuration here and part of the dynamics that go into explosive and pyrotechnics is look at how thick the wall is here compared to how
I
thick
was
it is
going to
here.
ask if
Yeah.
is that mock-up accurate, because it's so much thicker of a
And that's-
shell and it's not as round.
Yeah.
Correct. Cylinders tend to be more structurally sound. They actually can wrap string around them and make them even tighter and more bound. The more you hold or confine explosion, the more energy you're going to get out, the more noise. And when you make something like this, it's always mine's noisier than yours kind of thing. And so that's what they're doing. Now notice they did something different here. Here, these are bottom fused.
Uh-huh.
Yeah. I
Where's
see
the
that.
fuse at in this
It's
one?
on the
Oh.
top. Yeah.
Now, and the reason for that is you've got to penetrate through the here to get the time fuse in there. When the lift goes, sometimes that is strong enough that it can break and breach through here and send fire there, and that means that the shell blows up right
The
here.
energy with the, okay.
So they tend to time fuse this way, and what happens is it lights the timer here. It's on the top, but the brake or the lift is down here. The exploding and force going from that burning and thrusting it up is down here, and so it's easier to maintain the integrity there and security.
Okay.
So the lead fuse comes in here. It lights the timer here, but then you can see it carries around and comes out down here to light.
I see.
So so it's a little trickier that way. You can also not get this lit by doing this. Lift the shell and goes up, and then you get what we created here with the dummy here that just goes up and comes down.
Comes back down.
Which we call, the fitting title to this is a dud. And oh, that was a real dud because nothing happens in the
Right.
sky. And the display guys, then they have to be aware, okay, one of the things you do in the display is you have to watch and verify duds because you got to go get them. You don't want them left out there
Well,
because
that's what I'm thinking.
Yeah.
What if it's smoldering or something?
yeah, we've got a certain time frame that we watch and so forth,
Okay.
and you can tell. And sometimes, if it's really burning, and looks like it's active, you can throw a little water on it. But the bottom line is, we're in close when we're hand firing, doing things. We're in close with these things, doing the whole process. So if it's laying there in the ground because it didn't work in that, we just stay away from it for a while. If it blows up there, it can be a problem. But staying a distance away gives you the
Okay.
security. Now. These here give you an example of some other type things that are, we talk about ball stars here. Here you can see this is what's called a pump star, and essentially the composition's put in a tube and shoved out, and you create this tubular effect of material, and then you just cut it off and you get these cylinders.
Okay.
Those are going to burn longer. They're going to create the longer glowing
Oh,
things,
yeah.
and some of them go too long, almost go to the ground, so it's a matter of timing that.
So we can see that a
Right.
little bit too. That's okay. And so those long ones are I see where that's much different.
And so some of this you have to factor into what you're doing. A 3-inch isn't going to go high as a 12-inch. So the stars you put in here are going to have to be smaller than what you put here because you're not going to have the distance to the ground for it to burn out. And so these are going to be pretty impressive as far as they're going to come a long way because of how far this shell is going to go, because it's only a 3-inch. And you only put so much lift and put so much height to it. You can change that and vary it, but you balance it out. Then the other type is a cubical star that you see like this here. Again, a lot of composition there. And this one is known as a snowfall, and the way these come out is they're just going to come down and create this glowing, bright, white or gold effect that looks kind of like snowfall.
Okay.
Now, and on this, if I may,
Yep.
what we're seeing in the middle is the powder that ignites all of the stuff around it.
Correct.
And since those are thicker and more dense than, well, the balls would be, or larger than the balls, that's what's burning slower, giving us a different display.
The burn rate may be the same speed, but there's just not as much material there, so it goes out quicker.
Oh, okay.
Okay.
It doesn't last as long. It's just, it's endurance based on quantity of material.
And I see a lot more of the, the powder to get it up there. And is that because these are have a little more mass? Does it need more to propel it?
Yeah, and this may be, it's kind of interesting. maybe actually a 4-inch cylinder compared to 3-inch.
Oh, okay.
So it looks, it's awful
Yeah, it does
close.
look a little, yeah.
And see, that's part of the thing there. It's not like you can put a micrometer on here and determine, okay, how big it is, and that fits. The guideline and the standard is the tolerance you have here. And so the tube has to be able to slide in there, but there's a certain amount of gap that you want there. And so as long as it's not too big a gap for a shell, the 4-inch will work in there, but some 4-inches are a little bigger than size, like this here. See, there's
Slightly larger, yeah.
so as long as it can work in there and have the gap, because there's an excess of gas produced that'll throw the shell up. So when you actually are watching these launch, if you're close and can see it coming out of the tube, you will see the gas plume out here, boom, then the shell comes out. The gas goes so fast it gets ahead of the shell, then builds up enough pressure, the shell follows afterwards.
Okay.
So you've got a little bit of a play and tolerance there of how big it is. So there is more lift powder here because this is a heavier. You can just tell by picking up there's more mass here and stuff. Again, top fused.
I see that, yeah.
Now, the ones we see that the cities light, is that the larger, the 12-inch? Is that what, or are there a variety of sizes?
It's all variety of sizes. You're generally going to just see a few of these because they're so expensive.
That's those really big ones.
And
Okay.
yeah, so they really spread in the sky, and they usually get shot by themselves, so you can just see it. Very ornate, a lot of different effects in there. So you just, and it takes a period of time. It takes, it's going to be 5 to 10 seconds before the whole shell completely opens and out and then goes away.
Yeah.
And that's a long time when you're doing an intense kind of situation. So, but you're going to see 3-inch, or you're going to see that the lower level in that, then you're going to see 4-inch, and with that, then to do different effects, you can have the 3-inch, which is going to break at this height. You can have the 5 or 6-inch break at this height, and so you can see a multi-level kind of effect there. And then right over the top of it can be the 12 over above that.
And I understand they can all be in the same packaged all together, or they would be separate?
They're all going to be in separate tubes
Okay,
that match up
okay.
with their diameter
I see.
and separated there. And for convenience of the crew displaying it and working it out, most of the time they're kind of bunched together as far as the bigger shells and smaller shells, but sometimes there's a variety of them because they want to do multiple positions, and so they want to do 3-3-inch shells. So they got a 3-inch going here, left, middle, and right. Boom, the 3s go. At the same time, they might have 4-inch there that then 4s can go, and then some 6s there and stuff like that.
So there's an art to the timing. You said choreographed a while ago.
Yeah.
Right.
You meant that, didn't you?
Right, because what we've been talking about here is more hands-on and do it by hand, but then when you set this all up and put the multiple positions, then they actually connect that to computer, and then they actually can plug it into where the computer actually tells when the sequence to fire.
Oh my gosh.
And then they can even go back and create the thing, which many of the big displays you see on the 4th, they actually go back and they start with the music. And they actually add the fireworks to the rhythm, the cadence, the effect of what the music is producing, so that the fireworks simulate that in the sky, and then as the music plays, the shells are actually being launched based on that script.
So you said they start with the music and then add. I would have guessed it was the opposite way, that they would try to. Wow, that's really neat.
I've heard it balances out between different people, but I've heard for every 1 minute of fireworks, it's an hour of choreographic work to create the pattern for that.
Oh, wow.
And I've worked with the software and stuff, and it's really neat and easy to work with, because the music plays and you essentially just click and put where you want launches in there. Then you go back and know I've got a launch here. Now what shell want to go? Well, if you're talking about a song that's talking about blue, or I'm very blue today and whatever, blue firework shells. And so what size do I want to use? And then you pick from inventory and plug it in there, and you just create a whole database of what shells go and so forth.
Oh, that's neat.
And then to keep it all sequenced, the computer then fires it based on what you say the next cues are.
Cow.
And how is the computer firing? What's connected? What's it connected to?
Okay, what we don't have here to show you, but what they do then is, here we're talking about actually coming in an open flame. A fusee, some kind of torch or ignition lights this. This just cakes fire, and the fire goes right down in there, hits the black powder, shell comes out. With the computer fire, there's actually an ignition system that sends electricity. Firing system sends electricity to what we call an E-match. and that has a little bit of a pyrotechnic material on the end that puts a quick flame out. That quick flame goes into the here. So these are older style, but now the newer shells come that there's actually a little plastic port, so you can stick it right in there, cinch it on that port, and you're all electric fire ready to go.
And so the length, I imagine different manufacturers might have slightly different lengths of stuff. Do you have to put that into the computer to calculate, or is it fairly standard?
No,
for the fuse.
For the fuse.
The fuse actually is almost instant. What the timing is here. And so some of the companies actually go out and shoot hundreds of their shells, and they produce database that then they say, you want to buy our 3-inch shell? Here's the flight time. And so what they actually have to do is back time the flight time. So, okay, I want this shell to create this effect in the sky at this point of the music. So it's actually launched 2.5 seconds before that. And so at that point, boom. And so when you see a fireworks display where the rhythm is boom, 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 and the fireworks are going boom, boom, boom in the sky, they've all pre-launched so that they could break at that time.
Okay.
Wow.
But yeah, so there's a huge amount of data gathered based. And so the timers, these shells are going to have a different timer than these shells here. And then it's going to vary between the companies how they time in that, but you can get that. And so some of the people that are really good at choreographing and stuff like that, they don't trust anybody else's data, so they go out and shoot the very shells that they're going to shoot in the show and get their times and then work off of those times in order to create it.
Yeah.
Oh wow.
So a ton of time goes into it. So you got these variety of shells, and then like here is a 6-inch, this is an 8-inch, and then this is a 10-inch here.
I like that it's totally inert practice. It's really good, yeah.
So the one thing we haven't talked about is I just got to know is how do we get those different colors?
Okay.
And I have a feeling that's how we ended up in a chemistry lab.
Yep. They've made up a really nice sheet here that you guys can see there.
Yeah.
That talks about sparklers, and the interesting thing is when you're doing sparklers, most of the time it's just silver or kind of orange, yellow
Yes.
color, and that, which is the presence of iron. But the silver is a high concentration of aluminum and stuff like that. So that's the metal sparks in that. But the actual color comes back to basic chemistry. And as you can see mentioned there, it talks about the colorants. It's basically metal salts. And so you're going to have strontium, barium, copper, calcium, occasionally sodium. Sodium isn't used so much because it just contaminates everything. And so when we get into spectrum analysis and looking at our colors, when we're really trying to tweak it and get it better, sodium's always in there. Who put that in there? Nobody did. It just gets contaminated in there. So you tend not to use it for a yellow as much, or you find something that will work because it doesn't cross-contaminate. But sodium does give you the yellow color. So the flame tests we do in the lab, the color flame tests we do there, that's exactly what we derive this off.
Okay.
How neat.
So the thing is there with the flame test, you're just talking about the one material, it's salt in solution or a powder, and putting it into flame. Here now you're going to have to composite it so it can be a star or some kind of integral item that can be held in there.
So when I look at this, and so the purple, or well, red, white, and blue, because this is what would be a red, white, and blue that we'd see. Now, each of these different colors is a mixture then? When you say a salt, you could just explain that a little bit more, what you mean by that.
Okay, that's how we get the color. Those are the ingredients that get the color, but that basically is part, oftentimes, of the fuel. And what we have to do to get a pyrotechnic reaction work is have a fuel and an oxidizer.
Okay.
So sometimes the oxygen is on board with the colorant, but a lot of times it isn't. And so the oxidizer is like potassium nitrate, potassium perchlorate. That provides the oxygen that's with that. And so that's why fireworks can actually work in space. They don't need oxygen around them to work. It participates in our atmosphere when we do it, but they have all the things they need to burn on board. And so you add the strontium, perhaps strontium chlorate or carbonate or something like that, but then you add potassium nitrate or potassium perchlorate to that to give your oxidizer, and then to get it to hold together, you add something like dextran or something like that,
okay.
a starch
A
type
binder.
material that then's your binder, and that's what mixes it together then to create the ball effects or the cubicle or...
I was going to say, we were talking earlier, and you had said something I thought that was really cool. So I noticed that a lot of these include a chlorine, and you were saying that that can be beneficial when you light them up. How in what way?
Well, that's where this all developed from early alchemy and understanding about things like that and trial and error. As it got more scientific and the scientists got more involved in experimentation and instrumentation became available, began to say why. And what we found out is, why is this color better? What they began to do through spectroscopy and determine is the presence of chlorine enhanced the color, makes it more intense, more brilliant. And so they began to, and so we get into the whole flame chemistry, plasma chemistry that's going on in the actual live flame. And there are now pretty good descriptions of that reaction and the mechanism going on, where the presence of chlorine in each one of those situations makes the color more vivid. And so you purposely put in there, and in some cases when we talk about the formula, we talked about the fuel, the oxidizer, the binder, we also talked about the chlorine donor. So you could use like copper chloride. That provides the donor in that, but sometimes the copper in that configuration doesn't give you quite as good a blue. So you might put something else that gives you the chlorine and use another compound or metal salt of copper that gives you that, and then mix those together. And so then you begin to get all these variations and testing out to see what really works the best to give the most brilliant color. And so now there's literally hundreds, probably thousands of formulas that are out there that you can work off of and do, and that becomes kind of trade secret stuff. When somebody says, oh, that's a brilliant color, how do you get that? Well, I probably can't tell you that because that's ours. And
Neat, yeah.
I'm still tripping just a little bit. A little bit mind blown to think that that would work in space.
Oh yeah, well, and because so the perchlorate and the chlorate, so they've got those oxygens, and how does that work when they're, and you had mentioned that before, that this might be a mixture with some perchlorate in it.
Well, the perchlorate, the potassium just kind of breaks off, and so you end up with the chlorate molecule, and then that breaks down to produce a bunch of oxygen. And so it's the oxygen produces, same with nitrate. It produces oxygen. We break that compound apart, and that oxygen then fuels in there and so forth. And
that is so cool.
the space industry, NASA and them, they figured out a lot of those things because they realized, hey, we're going to need thrust, we're going to need to do things in space. And so they've developed the hypergolic situations where they just mix two fuels together and they flame and they create thrust and so forth. And the whole solid rocket booster and what's going on there is a solid composition material, not like this, but in a similar configuration. And they make it up, they pour it out, cast it in that booster, and then it burns and creates a tremendous amount of thrust and gas that lifts the rocket into space. In a similar situation, we're lifting these with a gas, just a much simpler design, just burning black powder.
That's cool.
And black powder then ends up fitting into that because you've got carbon, you've got sulfur and potassium nitrate, fuel and oxidizer. And the balance of that gives us the gas that we need. And if you can find it enough, that's what they used to do in the old mining things. It wasn't nearly as effective as some of the modern day explosives. They could blast apart with that. And so that's the chemistry and the configuration of how these go and that. So what I thought would be neat for you guys to do is, you see all this stuff here, is to see, okay, how does this get together? How do we do this? And so I actually have a ATF license, a manufacturer license and so forth, have all the components to put things together like this. And so to make a 12-inch shell, if you really love macrame and making things, you could make the cardboard hemis for it, or you can buy them. And so there's hemispheres for all these different sizes. So I brought in 3-inch hemispheres, and I brought in some inert materials, and I'm going to let you guys try to make a 3-inch shell. And then you can see these are pasted on the outside with that, and that's the old school way of doing it. Now they have machines that can actually do that, but there's still a lot of shells still hand pasted. I'm going to let you guys get a little gooey with some wheat paste and see how it pastes together. What it shows you too, and this is more of a, might have been hand pasted there, is the time factor. With the machine, because of how it's done in that, you can be done and launch the shell that night. With the hand pasting, it's like a couple days, maybe 3 days process, because you put one layer on. You can't keep putting a layer on because it'll just all stay wet and fall off.
Yeah.
So you have to let it dry one day, then you come back and put another layer on and another layer on, and then you're ready to proceed on. And that's just doing this part. Then you have to come back and put the lift on here and do that.
Oh, wow.
And you can see here, probably a 12-inch shell takes about a pound of black powder to launch it at height.
All right, we made it over to the lab, Paul. What do we have here?
Okay, you remember we looked at the mock up there?
Yes.
What we're going to do is similar to that, and what you're going to try to do is get all these balls essentially on the outside of the hemisphere there.
Okay.
Now, we don't have live stars. These are just black beans, so they kind of represent that. So how do you think you're going to get that, a whole layer of those around the outside there?
Glue.
Well,
Glue 'em in?
you could do glue, but you're thinking the whole process of how long it's going to take to glue things and do things. How might you do it quicker?
I'm thinking maybe start with a layer and then put some of this and then build it up, kind of like you're laying bricks.
Okay, the layering is the key thing. So
Okay.
dump those in there and start to layer it as best you can. You both got yours there. And then rather than dump other things in there, what you end up doing is holding it in place with some tissue paper, which I'm going to give you. So bring it all the way up the sides there, Steve, as high as you can go, because you see how these are going. They go all the way down and all the way back up the other side.
Wow. Okay.
So Steve will be a little easier once you get those. Then you're going to put that tissue paper in there to kind of hold it in place. Sarah, with yours, you've got the time fuse sticking up in there.
Oh yeah.
So that makes it a little more challenging. So we'll give you a couple pieces that you can kind of get it started there, and
Okay.
then you put the tissue paper in there to kind of hold it in place. That's the idea, Steve. Okay, you're getting it there, Sarah.
Okay.
See?
Now-
That could be a
Oh, I see what you're saying.
mortar
Yeah.
maker.
So now, this is just kitty litter, but now
Okay.
what would go in there is going to be your burst powder, your brake powder, and
Okay.
that's what holds things in place. So dump some of the kitty litter in there,
All right.
and then you're going to bring that tissue back over the top of that.
Well, that's pretty dainty.
Well,
And you want enough there to almost come up to the surface of the hemisphere to fill it up,
oh, okay.
to hold things together. And that holds those stars in place. But then you'll see that's how we can get this to go together, because that's going to be the next challenge I'm going to throw at you.
Oh no.
How are we going to get those two hemispheres together?
Oh, maybe I'll need a little more.
Because that's only half of it. We know there's another hemisphere, so how do we get that together?
I'm thinking probably another thing of tissue.
That would work, or we can use a 3x5 card.
Ooh. Oh, and then like a. Like you're yanking the tablecloth.
A magic trick.
Right. And the way Steve's got his and what you're doing with yours there, you potentially can just put those together and do it, but we'll do it with the 3x5 card because that's a
Yeah.
little more successful. If you've got them really packed tight and they're tight, sometimes they hold fairly well in that.
I just want to point out that mine's tighter than yours, I think.
Oh my gosh.
The situation is interesting in that he can have an absolutely gorgeous setup there inside, and we're going to blow it apart, so it doesn't matter.
There,
Is what's
see?
going to happen in the fireworks. So
So what I'm hearing is there's no style points. That's what I'm
that's
hearing.
right. The style's going to get totally burned up. All right, so Steve, put that on
right.
yours, and one or the other of you can decide who's going to flip it over to. There you go.
Oh, nice.
Good?
Yeah. Okay.
You ready?
Yeah.
Make it happen.
Okay, now let me show you what we realize is these hemispheres are not exactly the same. So we purposely try to find a couple that match up.
Line.
So in order to do that now, it's really tough to know where to go. So we put those lines on, and then when we get to this point, we line those up, and then I put 2 over here, so we're lined up there. And you can see now, by looking at that, it's pretty good.
We're just down here on
Yep.
the camera.
Get it to where they can see, to where they match up pretty good.
Nice.
Yeah.
Well, that was pretty smart to.
So, but that was done previous to all this. So the first step you actually do, which I did before we came to this, is match our
them
hammers,
up.
match them up.
Okay.
So then the next step is take the tape, hold that, and securely tape the hemisphere.
Okay.
Now I'm thinking if we're doing the in the paper mache style that you had mentioned,
Correct?
it
Then really work that down tight, get
Okay.
that tape to really tight.
they actually make these through like I said, like a paper mache type making now.
Yeah, there's some people are real purists that want to make their own hemispheres because they know the integrity and they can make them thick as they want and so forth. They'll use a heavier body paper and they've got what they a mold that they use, and they create it over the top of that and build it up. And as you saw on the one shell there, how thick that was. Some people want a
Yes.
thicker hemisphere, and you can buy prefabbed, but they're only certain thickness. So
Okay.
I see.
they do that and that. So just so you're aware, if we put it on a machine and it tapes it up, we're going to lose our time fuse hole. There's no time fuse here. That goes in after you've done the pasting and that. So the ingenious people that did the machine discovered that they could buy these little tiny cylinder magnets and put that in here with a piece of tape over the top. You run it in the tape machine, it rolls it all around, tapes it all up like you're going to do with the hand paper there.
Okay.
When you get done, you bring another magnet back, grabs on the top there, and then you just score around the upper magnet, you pull it out, you found your hole.
That's clever.
Oh.
Because otherwise, where is it at?
Yeah.
Is it this side or this side? And then you're probing around and digging around, and
man.
so that you got a whole slew of those magnets you just put in there and run it on the machine. So we could have done that with this here. So when you get done pasting, you could find it as well that with this. We're not going to take the time to get it all pasted up, but if it went over the top, that's what you have to do to find that. The time fuse gets put in after all the pasting's done, and part of the reason for that is this is going to add a lot of moisture around the outside. The time fuse sticking outside, you can end up getting it too wet.
Oh.
And so the shell's completely dry before you put the time fuse in there, and most of the time the time fuse is glued in there with hot glue. Around the outside. And again, you want good integrity there because this is going to be sitting down with the black powder underneath it. If that isn't secured well in that, you can shoot flame inside, and then you get it pre-igniting, and you don't want that. Okay, so there you've got a couple pieces of paper, and you can see I just got some calendars in here from the university and so forth. And so you can see the difference. This is the paper from there, and this is the paper I brought in, and so you'd use different poundage of paper and stuff like that. Either one will work.
Okay.
See how those wrap around there, how long they go. We may want to cut those in half and just,
Yeah, maybe in half.
yeah, and then, so cut those in half.
Okay.
And then all that is done usually, some people use wallpaper paste and different things like that.
Oh.
But essentially, this is just a straight wheat paste. Some people that are real purist about it actually makes their own flour paste, which means they got to do boiling water, add the flour in there, work through all that, filter that out, and so forth. This is just a commercial wheat paste and that. So what you do is put those, not this,
Okay, nothing.
These, right?
those in there,
Okay.
and then work it around with your hands to get paper on there or paste on there, and then you break it. Work it around to where it's really flexible,
Okay.
and then from there, each of you can try wrapping a piece around the,
And just pour.
yeah.
Oh, I like that consistency. Oh, maybe we need more.
Yeah, and just work it in there and then manipulate it.
Okay.
You want to just soak it up, and it would be nice if you can have this preset and be able to do it and stuff, but the trouble is wheat paste doesn't hold up real well, and if you get your paper already, then it starts to biodegrade and do stuff like that. So pretty well you make it up like this and you get ready.
You have dry spots. You're in a hurry. I don't trust your fireworks.
So, and then once you get it worked in and you think it's good that way, then strip all the paste you can off of it.
Okay.
And then come to actually putting it around there and stick it on there and paste in the shell. And you'll have to pull it out of there and, yeah, manipulate it around that way. Then
Do you paper mache much?
Nope.
You don't too, huh?
No.
We do at our house. It's like a hobby.
Is it?
And so and you can see there, we probably should have, I just cut them random, but probably should have put them a little narrower because it's easier to get them to fold down. And with the machines, depending on the size, I should have thought of that. With the machine on the 3-inch, you use a 1/2 inch tape. And then you get into bigger shells, you move to 3/4 inch tape, and then bigger shells to 5-inch. But you can see what Steve's doing there.
His expert skills here.
Because you can see how the outside of that one there is really laid down, and that's what you end up doing.
I see. Okay, well.
That's the whole pasting operation, and that's critical because you have to confine the reactions long enough for it to ignite all the components before it blows it apart. So you put the right amount of burst powder in there, then you have the right amount of integrity with your paper on the outside to secure it.
But we're only going to be able to put on like a layer at a time. Then it has to dry entirely, right?
Yeah, it doesn't have to be 100% dry, but usually overnight it's dry enough, then you can go to the next layer.
So it's literally to make a 3-inch mortar. It's going to take the better part of a week.
Oh yeah, so what they end up doing is staging it, so they'll go through and paste one set, then they'll paste another set, and then they come back and reverse through that. But oh yeah, and so they have, what they'll do then is once it gets done is then they have these drying racks and they put them outside, so that speeds it up to dry it and so forth. But the weather's a factor in that. If it's really humid and things like that, they have some drying machines and things that they could do. But yeah, there's a lot of material just sitting around drying and processing, and takes up a lot of space because there again, you don't want to have all this stuff in one space and then have an incident that it's all. So you diversify, you spread out.
So speaking of incident, what type of license, so what type of training do you have to go through in order to get licensed? So here's 2 questions there. To do something like this.
The whole regulatory situation is to get a license, you have to have a place you can store this stuff legally.
Okay.
That's all guided by the ATF.
Oh.
And so they would have to give you a license, that you fill out paperwork. You're going to have a background check to make sure you don't have a felony charge against you. And then from there, as far as training and stuff like that, they don't really go into that. It's more, do you have the proper storage for it and where you can put it? And to do displays and actually do the fireworks public displays and stuff like that, there's the requirement of training and background and experience and stuff like that, because you can't get the permit to do display unless the fire marshal signs off and says, okay, this person is trained or has experience and can do this. So for the ATF, they're going to want to know where you're going to store it, and they've got all this protocol of what it is, and it's got to be separated away from things, it's got to be secure, just a whole bunch of things that go there. And
then I'm guessing for some of the materials, it's a separate license then to be able to actually acquire and purchase.
If you have the ATF license to manufacture, that allows you to get any materials you need. Most of the materials, like we talked about the color stuff, any person can get that as long as they can convince the supplier that that they're doing something of a legit matter and so forth. The material that's very energetic, the silver compound that I showed you in the one shell and stuff like that, that's been used illegally for making M80s and stuff like that, and so that is more regulated, and so those suppliers won't sell you that unless they'll sell you real small quantities, but anything of quantity you have to have an ATF license. We realize when we work with this stuff that there's a risk, and so the focus is we're not going to get rid of risk, we're going to manage it. What's the smartest way to do this? And that comes back to the same thing that we do in the lab and stuff like that. There's some risk to that, but we manage it. We follow through with things that way. And that's been the fascinating thing for me, coming from it from the scientific aspect as a chemist, to realize the early people in this were all trial and error, no risk management, and then because it was secretive, and they didn't want to communicate, nobody is learning from each other, and so the same errors are being repeated from generation to generation. Science came involved, and then we began to start communicating better and saying, hey, let's do some risk management. Don't put these two compounds together. They tend to go off on their own. And So science has helped get that information and share that.
I really like the way you point out, with everything there's risk.
Yeah.
And risk management is a priority in what we do. And so this time of year, looking at fireworks and stuff, I think it's a really great thing to remind other people. Yes, in these larger mortars and stuff, there's certainly risk in building and definitely in lighting them off, but there's also risk in the things that they're doing.
Yep.
The things they're doing. I mean, sparklers. I mean, there's more kids get burnt with sparklers
Yeah.
Oh, yeah.
than any other fireworks.
That's the greatest injury cause in fireworks around the holidays or throughout the year is sparklers. And it's interesting, they finally got the picture and thinking about that to where now they're trying, it doesn't work as well, but you're finding more and more sparklers with a wood stick.
Yes.
Yes.
And you know, that was one of the things that caught my attention early on, is realizing we're heating this thing up, we're holding it, and you don't think about where you're holding it, thermal conductivity, boom. And,
Well, and kids, if you're just handing them off to the kids, they're not thinking about that at all.
yeah.
So,
And there's some really great safety videos out there about doing fireworks with sparklers and stuff, and just some basic things there. What do you do with it afterwards? You know, throw it in a paper bucket with paper in there. You know, so you know, it's just simple things. Make sure it's a bucket can handle heat. Have a little water. Kids throw it in there. And there again, what are we doing? Risk management, thinking about how to process and deal with that. And so that strategy, I think, is really apropos for all of life. And too often, we tend to just go about things without thinking about that, and then all of a sudden get caught unawares and realize, whoop, wasn't thinking ahead there to manage that risk and so forth.
okay, I got a question. What do you recommend, or what's your favorite way if you're going to do some fireworks to light them? What's the
For regular
safest for
people, right?
for the lay person, the person that just wants to do some backyard fireworks on the 4th of July? I remember as a kid we used to get punks, I think is what they call them, but now it seems like they don't.
You can still get those. Some of the fireworks companies have them when you buy from them for your backyard fireworks.
Well, all right, what's a punk?
That is it's a wood material with a little bit of binder in there.
Okay.
And it's flammable, not extremely, and it glows. So
Yeah.
essentially it's like a wood stick glowing, but it's a composite that they make and put onto a stick, and it tends to hold fire in that. I like, and we do use it some for public displays, but is a propane torch with a trigger mechanism on it that you can click on and fire and off. And so then you can go out there and light it. The disadvantage of that is it doesn't produce much light. And that's one of the things you find out doing a public display. If somebody's lighting with a road flare, there's a whole lot of red light coming out of there. And so you've got some ability to see just by that illumination. And especially the lighter, he can see what the light just with the flare. With the torch, you're going to need another ancillary light or something like that. But those are really nice because it's only on when you're doing it. With the guy at the flare and other people working with him to load shells again and do it in hand display and stuff like that, you always got to be aware, ignition source here, I'm carrying flammable materials. So with the torch, it's easier on and off. And for the backyard thing, you're going to be shooting something and watching and so forth, so it's easy to trigger and back and forth there.
Okay.
The punk's nice, but they tend not to sometimes stay on fire, and so you have to relight
Yeah.
them. And,
Yeah.
the one thing it isn't good, which some people do in that, is getting down there with your little lighter or doing things like that and so forth.
What about those long lighters that we see in the stores?
That's a better option.
That's
because
what we usually use at our house.
you got a better option there because you got distance. The trouble with the small cigarette lighter or small lighter is that when you light the fuse sticking out like that, it generally is going to shoot fire out the end of the fuse. And if you're lighting this way, that fire comes right onto your hand, and you
Yes.
can burn your hand. So if you light it at an angle, you're all right that way. But if you're using the fireplace lighter, the longer ones, you're a distance away. That helps that way. And then it also helps, you've got to get right down there, you got to crouch completely down there, light it, and then you've got to step up, you've got to turn away as it lights, and that's just easier for tripping and you know, stumbling and stuff like that, where if you can reach out with the longer lighter, then you can do that.
Okay, thank you.
Thank you
This
so
was
much.
so cool.
This was very fun.